I'd like to demonstrate how to calculate the resultant force due to hydrostatic force with an example. In this particular example, I've got a reservoir with a gate. The gate itself is 2 meters wide. That would be going into the board by 1.2 meters tall. That would be this dimension here. And the gate is 3 meters below the water surface. And again, what we're after is how to calculate the resultant force. Now, there's two different approaches to do this. With the first approach, what we're going to do is we're going to use the statics approach. So I'll go ahead and do that up here. So using the statics approach, okay, this could be a refresher for you in statics. Okay. With the statics approach, what we're looking at is, if I kind of redraw this, if that's my water surface, right, and down here I have the gate. Okay, make it a little larger. Okay, so if we look at the pressure distribution, remember in the previous lesson we learned that pressure is a function of depth. So at the water surface there's no pressure. As we increase depth, we increase pressure. And so the distribution looks something like this. Okay, the pressure distribution. Okay, so if we look at this specific piece right here, what we see is we have a trapezoidal distribution. So here is the gate itself. Let's kind of draw that in as a gate. Okay, and then we have a distribution that looks something like this. Okay. Now, the easiest way for us to handle a trapezoid distribution, if you recall from statics, is to break it up into two different objects. We have a rectangle, and then we have a triangle. The rectangle will have a force associated with it. We'll call that F1, and the triangle will have another force associated, F2. Okay. Now for the base of this, what we need to do is we need to calculate the pressure at this point. I'll call it P1. Okay. So as I've just mentioned, pressure is a function of depth, and actually what it is pressure is equal to the specific weight times the depth h. So at the top of this gate, I'll just say at the top of this gate here, we're 3 meters down from the water surface. So we're going to have the specific weight of water at the depth of 3. Okay. For the pressure down here, it's a similar calculation, but in this particular case, at the bottom of this surface here, we're at a depth of 3 plus 1.2. So we have gamma water times the total depth of 4.2. So now what we have to do is we have to solve for the magnitude of these forces. Okay. F1 is going to be equal to, okay, so we think back to statics when you're doing distributed loads, okay. The magnitude of the force within a distributed load was the area of the distributed load, right? So the area of this triangle, I'm sorry, this rectangle, it has a base of gamma water times 3, okay. It has a height dimension of 1.2, and then going into the board, it has a dimension of, what's it, 2 meters, okay? Okay, so let's see, that gives us F1 is equal to, you have 3 times 1.2 is 3.6 times 2 is 7.2. So F1 is equal to 7.2 times gamma water. For F2, we're going to do a similar calculation, but instead of having a rectangular distribution, we have a triangular distribution. So for F2, we're going to have, again, now this base right here is going to be the 4.2 gamma minus the 3 gamma, right? So let's see. First of all, we're going to solve for this piece here. So we have a triangle. So for the area of a triangle, we have 1/2 the base. This piece here will, again, will be the, it's going to be gamma water, and then you have the 4.2 minus the 3. Okay. The height of this, again, is going to be 1.2. And then going into the board, as we had earlier, we have 2 meters. Okay. So let's see, you got the 1/2 here and the 2. So I've got basically 1.2 times 1.2 gamma water. That comes out to be 1.44 gamma water. So my total force is going to be the sum of those two forces, which is equal to 8.64 gamma water. Okay. At this stage, well, let me go ahead and just put in the values. If I use a value, let's see, we'd have this again, this would be 8.64. Technically, this was cubic meters, right? Because these were all meter dimensions. And then if we use a value of, say, 9.81 kilonewtons per meter cubed, okay? So if we calculate the magnitude of that force, we'd have 9.1 times 8.64, which comes out to be 84.76 kilonewtons. Okay. So you can see the stacks approach was pretty extensive. We had to go back to old school. We had to break it in terms of rectangle and a triangular distribution, sum up the forces. Okay. Now, if we use the fluids approach, which I'm going to go back over here and do, because it's actually a very simple approach and we don't need a lot of space to do it. Okay. So with the fluids approach, it's a formula that says the resultant force is the gamma of the water times the depth of the centroid times the area of the plate. The only calculation involved in this one that can be a little complex at times is calculating the depth of the centroid. The depth of the centroid is this dimension right here. Okay. So literally, we're thinking of a rectangle here that's 1.2 meters tall, and so we want to get to the depth of that. So we have gamma water. Okay, our depth of centroid is going to be the 3 meters plus half of this dimension, which is 1.2. So we're saying 1.2 over 2. That times the area of the plate, right? Because this force is acting normal to that plate. So it's a 1.2 by 2 meter area. Okay, and this comes out to be exactly the same value. We get 8.64 times gamma water, or the resultant force comes out to be 84.76 kilonewtons. Okay, obviously this makes us very happy because we got the same answer using two different techniques. I think all of us could agree that even though the statics technique is fundamentally very sound from an engineering perspective, you know, if you don't know what to do, you do what you know, and this would be a really, really good technique if you couldn't remember. But at the same time, if you have this in your toolbox and you remember this formula, the fluids approach is a lot easier. And that concludes our example.